Hello and welcome. This is Roshan, and today we will be discussing yet one more application of the Euler-Lagrange equation. More specifically, we will be looking at what is known as the Fermat's principle. So we know that light travels in a straight line from point 1 to point 2. Light, as long as the refractive index of that medium is a constant, light travels in a straight line. But when light encounters an obstacle, such as a mirror, it's going to reflect. And it does reflect following certain specific laws. Right? So particularly there are two laws of reflection that it obeys. Let's look at what those laws are, and then we will go about deriving those laws, starting with what is known as Fermat's principle, which is based on the idea of from calculus of variations that we have been discussing in the last two videos, which involves the use of a particular integral which will be minimized, and in trying to minimize it we arrive at our solution. So let's look at it. Let's first recall the principle of least action. So if you remember, in the last videos, we started by constructing an integral of a function of y dash and x, which we called s, and the integral went from x1 to x2, and our task was to minimize this integral. One of the ways of arriving at our solution was to minimize. Of course, the other possibility is to maximize it. But let's focus on the minimizing part, right? So let's say we want to minimize this integral, and in trying to minimize this, we arrived at an equation which ultimately it was known as the Euler-Lagrange equation. And this equation is very powerful, I told you earlier. And in fact, the principle, right, that leads to that equation is, you might agree, also very, very powerful. Right? So let's look at how we can directly use this principle of minimizing a certain integral, which in this case is sometimes known as the action integral, and that's going to lead us to something profound. And here we're interested in particularly light. So when you consider light going from one point to another, from point 1 to point 2, we know that light is going to take a straight line. It's going to take a straight line path from 1 to 2, but that is only under certain conditions, particularly when the refractive index n is a constant. If it's not varying from place to place, more particularly, a better word would be uniform, right? So it's you can think of a refractive index as a function of space x, y, z. And if that is going to be that's going to be uniform, right? The light is going to take a straight line path. And there's something that we have been learning since our school days, that light travels in straight lines, right? But when light encounters an obstacle, think of a mirror or a wall, light is going to bounce off the wall or the mirror. And in this process, this bouncing of light itself follows certain very precise rules. And these are the laws of reflection. So let's first take a look at what these laws of reflection are, and then we will state what this principle of least action is. And then we will go about proving that light does obey those laws. Right? So we have a bit of a journey here. So let's take a look. Firstly, what are the laws of reflection? So let's imagine there is a wall or a mirror. So there's a rough side of the mirror, and on top of it is the smooth side where the light bounces off perfectly, right, without any roughness, right? So we have a smooth surface. So we have an incident light coming in, and the question is, in what direction is the light going to reflect, right? So it has a number of possibilities. In fact, there are infinitely many possible paths that light could take, but light chooses to take just one out of those infinite possibilities. And which path is that? Right? Or at least it appears that light is taking one of those infinite possible paths. So which path is that? So to specify that path, we have to measure angles. So one way to do that is to drop a normal, which is basically an imaginary line that's perpendicular to the reflecting surface, which we will refer to as the normal. And there's the angle that is made by the incident ray with the normal, which we will call the angle of incidence. So for now, let's just call it θ1. And then there's the angle of reflection that is made by the reflected ray with the normal, and that we shall call as θ2. Now there are two things that these laws of reflection assert. In fact, they're therefore referred to as the first law and the second law. It doesn't matter what the order is. The order, what you call as the first law, can vary, right? Depending on different textbooks, they use different conventions. But the first law of reflection can be understood as being that the incident ray, the normal to the plane of reflection here, and the reflected ray all lie in the same plane. So the incident ray, the normal, and the reflected ray, they all lie in the same plane. Now, what do you mean by same plane? Does it mean that it's the reflecting surface that is the plane here? No. The plane is the plane of the screen, what you're able to see here. So the incident light, the reflected light, they're all lying flat along with the normal. The reflected light, in other words, is not sticking out of the screen or going into the screen away from you. It's staying within the plane of the screen. So that's the plane that we're referring to here, right? So that's the first law. So light sort of bounces and then it keeps going straight. It does not deflect one way or the other way, but it keeps going straight. So that's one casual way of putting it. And then there is this second law of reflection that says that the angle of incidence, which we're calling θ1 here, is going to be equal to the angle of reflection. So these two angles, θ1 and θ2, are going to be equal. So that sort of makes light go in a particular direction. In other words, light, if it has to obey both of these laws, has basically no freedom left. It has no other choice. So these two laws together pinpoint a particular direction in which light is going to reflect, or light is going to travel after reflection. So these are the laws, and these have been known from experiments, right? So these have not really been proven theoretically, at least initially, right? Historically, they were found from experiments, and these are well established. We haven't found any violations of these, right? And this seems to be true in any case, whether this works even when you have a rough surface, not just a polished smooth surface like a mirror. Even when you look at anything in your room, for example, right now, whatever you see around you, right, is probably because of some reflected light. Either it could be the sunlight coming from the outside, which is also reflecting across, different objects that are inside your room right now, or it could be a light that you have, an artificial light that you have turned on, which also is making things visible in your room due to reflection. Right? So the light falls on the objects and it reaches your eyes and you're able to see, right, the objects. So these are the laws of reflection which are operating everywhere around us. Now, what does Fermat say? Let's consider what is Fermat's principle. So Fermat's principle claims that the path that light takes from one point to another point will always be the quickest path. It may not necessarily be the shortest path, but it most certainly will be the quickest path. Right? So there's a small difference between shortest path and quickest path. We often like to think, okay, we have point 1 here and point 2 here. Of course, the shortest path will also be the quickest path, right? But not always. In fact, when you consider light to be bouncing off this mirror, so you can imagine light taking all possible paths. And so we're not considering light going directly from 1 to 2, but rather after having reflected from the mirror, and of all the possible paths that light could take, light is going to take one path of all of those, and that will be the one that looks something like this. So this blue one. Of all the paths that light could take, bouncing off the mirror, it's going to take this one path, and this one path will be the one for which the time is the least. So it's the quickest path. And there might be other paths that may be shorter, right? But the quickest path is the one that light's going to take. And of course, in this particular case, it happens that the quickest path may also be the shortest path, right? But we are interested in the quickness, the time. So what Fermat principle says is that light always takes the paths with the shortest time. And that may or may not be the shortest path, but it certainly is going to be the shortest time. Now, how does this relate to the principle of least action that we are aware of? So you can think of light going from one point to another point. Let's imagine a tiny displacement ds that it's going to undergo. And you can think that light traveling at the speed of light, c, right, which is 3 × 10⁸ approximately meter per second, takes a certain time dt. Right? So this is the distance that it's trying to cover in a certain time dt, traveling at this speed. So whatever path that the light is going to take, or whatever the time that it's going to take to go from point 1 to point 2, you can imagine dividing that into a large number of such tiny time intervals dt, and then adding all of them up. So you're going from time t1 to t2, and t is the total time here. So we have a situation here which looks quite similar to the integral that we discussed earlier, and which we have discussed in our earlier videos. So therefore our task here is very clear. We want to minimize this time, and therefore we have to minimize this integral. So it all comes down to minimizing the integral. So this time can be rewritten using the formula for distance, or rather for speed. So since speed is defined as distance divided by time, we can rewrite time as distance by speed, where we are referring to speed of light here, right, by v. And therefore one more thing that we can do here is to introduce the concept of refractive index. A refractive index is a number that is associated with every medium. Different media have different values of refractive index depending upon what the speed of light is. And so we define refractive index as c by v, c being the speed of light in vacuum, which is 3 × 10⁸, and v is the speed of light in that particular medium, and therefore whichever medium we are focusing on. And so v can therefore be written as c by n. So let us replace that here, and what we end up with is c by n, or since c is anyway a constant, so we have integral of n times ds. But then n is also constant here, right? So we're going to assume we are discussing reflection here, which means that light is moving through a medium, hitting the mirror, and after reflection it's still traveling through the same medium. So n is not really changing here. So n is also a constant of integration, is a constant here, and therefore need not be integrated, and we can keep it out. So now our task boils down to finding out what the what this is, right? So to minimize this integral, and minimizing this itself will, turns out, lead us to the two laws of reflection that we discussed earlier. which are empirical laws, which have been deduced from experiments. But now we're able to deduce it theoretically using Fermat's principle and our task of minimizing this integral, therefore. For that, we need to set up our problem a bit more precisely. We have to be very sure which way is light coming in from, where is it hitting the mirror, and which way is it going to go. And to do that, let us consider a coordinate system. Let us introduce a y-axis and an x-axis. And here, let us consider light coming in from some point P1. Let's say that point is on the y-axis, and it's coming in and hitting the xz plane. So you can imagine there is also the z-axis, and so it could be hitting this anywhere in the xz plane, but then it's going to bounce off and go to some other point P2. So let us mark the coordinates of these points to be specific. P1 is on the y-axis, which means its coordinates are going to be 0, y1, 0. Right? So its x and z coordinates are going to be 0, whereas P2 here is in the xy plane again, and so its coordinates would be x2, y2 and 0. Whereas the point Q, where the light is bouncing off, let us, for the sake of generality, assume it to be anywhere on the xz plane. So you might already be guessing what our point is then to prove, right? So our aim is to prove that this point Q is not anywhere on the xz plane, but exactly on the x-axis. So that this whole thing, the incident ray, the reflected ray, and if you draw a normal, they all lie in the same plane. So our task is to show that z is 0. But for the sake of generality, to start with, let us say that this is some x and 0 and z. Now y is suddenly 0. The y coordinate is 0 because it's somewhere on the xz plane, right? But z could be anything and x could be anything, right? So by fixing z and x, then we are deciding that a specific path that light is going to take when it's going to reflect, right? So we know the starting point and the ending point, P1 and P2. The question is, what path is it going to take? So I hope you appreciate that if Q is varied or if it's moved around, that's going to change the entire path of the light. If Q were to be somewhere here, right, so light would be taking a path that looks like this. Whereas if Q were to be further away from the x-axis, somewhere here, so it'll have to come out of the screen, hit this point, and then go away from us again, right? So light can do all sorts of things. In principle, right, we can imagine light to have all these degrees of freedom, but what we would like to show is that that is not true in reality, that light does not take any of those paths, but it takes this one specific path that obeys those two laws of reflection. So let us go about proving that. So let us continue with the integral that we had written down earlier, integral n by c and integral of ds. Now let's break this integral down into two parts. First is the initial part where you have the incident ray going from P1 to Q, and that is I'm going to indicate that with the limits. So we are going from 0, y1, 0 to x, 0, z, and there's the second part, the reflected light, which is going from x0 z all the way till x2 y2 0. And I hope you remember our task. The bigger picture here is to minimize this integral. We want to minimize the value of this, and that in turn is going to lead us to the loss of reflection. So in order to minimize this, firstly, let us write down what these distances are. Now light is traveling in a straight line, right? There's no doubt about that. And therefore we can directly use the distance formula to write down what the distances are, right? So initially P1 to Q, the incident light is covering a distance of x minus 0 squared, 0 minus y1 squared, and z minus 0 squared. And I'm just directly using the distance formula. knowing that this is a straight line, and this integral ultimately will give us the total distance between the 2 points P1 and Q. Similarly, for the second integral, it's going to be again the distance, but this time it's going to be x2 minus x squared, y2 minus 0 squared, and z minus 0 squared. Okay, so we seem to have been done with the integral, right? And so what we end up with is something that looks like this: x squared plus y1 squared plus z squared, and this here is x2 minus x squared, y2 squared plus z squared. So this is our time. Now remember, Fermat's principle says that this time has to be minimum, right? So you have to minimize this time, and one way to look at minimizing time is to look at how time varies with z. Right? So you can imagine that if I alter the value of z, I'm basically changing where light is heading on the xz plane, and that in turn is going to affect how much time it takes, the overall time it takes for light to go from P1 to P2. And so let us look at how t varies with z. So we would like to focus on variation of t, the time, and t being the total time that light takes to go from P1 to P2 with z. And certainly our aim is to minimize the time. Therefore, we would like to consider this case where the time variation of time with z is going to be 0. That's when we can say that time is minimum. We want, in other words, the value of z that's going to minimize the time of travel for light. You can also imagine in terms of a graph. If I plot a graph of t versus z, you can imagine you get a curve, something like that, and I'm interested in the value of z, the particular value of z that's going to lead to a minimum time. And the best way to do that is to differentiate and equate it to 0. So here we are supposed to perform a partial differentiation with respect to z, and let's do that. So n by c is a constant. Now how do you differentiate a square root? It becomes 1 by 2 times the square root of whatever that is. I will for the moment get rid of this graph so it doesn't come in the way of our equations. And times, using the chain rule, it's going to be 2z, because all the other variables are treated as constants here, x and y1 and y2 and x2, these are all constants, right? Plus differentiating the second part as well, you have 2 times of whatever this square root is times 2z, which is going to be 0. So continuing, we have z as a common factor, and we end up with something like this: 1 by square root of x2 minus x squared plus y2 squared plus z squared, and equal to 0. Now we have a product of 2 factors which is equal to 0, which can be true, as you know, mathematically only if one of them is 0, at least one of them is 0. So we have a possibility that either z is 0 or all of this brackets, what's inside the brackets is 0. Now what's inside the brackets need not be 0. Right? It's not a general condition. In fact, if you look at it, if you rearrange it and rewrite it, it looks something like this on cross multiplying. That, and if you square it, you can even get rid of the square roots. What does this represent? This represents the distance, right? Distance, the first term here is the distance from P to Q, or P1 to Q. And the second one is the distance from Q to P2. Now these distances need not be equal. If you look at the figure, clearly they are not equal in our figure. P2 could have been anywhere else, right? So it doesn't have to be equal. So this, the second factor being 0 is not a requirement, right? In fact, it need not be 0. These need not be equal, so this need not be 0. That leaves us with the only choice that z is 0. And if z is 0, that means the point Q can't be anywhere on the xz plane. It can only be on the x-axis. So we have therefore confirmation of the first law of reflection, that the incident ray, reflected ray, and the normal, if you imagine a normal here that's drawn, they all lie in the same plane, and this can happen only if Q lies within the XY plane and it doesn't come out of it. And that can be true only if Q is on the x-axis and Z is equal to 0. So this here is therefore a confirmation of the first law of reflection, that the incident ray, normal, and the reflected ray, they all lie in the same plane. What about the second law to do with the angles of incidence and reflection? For that, let us look at the variation of the same time, right? The time of travel of light, not with respect to Z, but rather with respect to X, right? So we'd like to know where on the x-axis. Now that we know that this point Q is on the x-axis, we'd also like to know where exactly this point Q is on the x-axis. Is it closer to the origin, or is it closer to P2, right? Or is it exactly midway? Where exactly, right? And for that we will have to specify the angles, right? So as usual, we'll call this θ1 and θ2. So as you know, our task will be to show that θ1 and θ2 are equal. And to do that, let us consider variation of t this time, but with respect to x. And let us minimize that. And minimizing that means we're making it 0. So what we're looking at here is, just like earlier, what we did with z, we're now looking at variation of t with x. And we want this variation, this slope to become 0, indicating that you've reached minimum value. Right? It could also again be maximum, but here we're talking about the minimum. So what is that going to be? Let us again differentiate t with respect to x this time. So n by c are constants. Again, differentiating, the first part remains the same. It's going to be 1 by 2 times the square root times, using the chain rule, there's going to be 2x. Whereas here again it's going to be 1 by square root of all of that, times, using the chain rule, it's going to be twice of x2 minus x, and all of this equated to 0. Right, so what we have is this, and now again we can cancel 2, by the way there's 2 here as well, right? So 2 cancels, and we get, now you see we can't really take x common factor. Instead we'll have to realize that there's just one factor which is equated to 0, which means I can rearrange, n by c can be sent away, and then we have this equal to minus of x2 minus x by square root of x2 minus x squared plus y2 squared plus z2 squared. Now what exactly is this, right? So this seems to be a ratio of 2 sides. In fact, these are ratios of 2 sides of the triangles that are forming in the figure. So let me redraw the figure, or rather bring this figure here so that we can analyze it. Let me bring it down. And what you notice here is this left hand side, x divided by this, is nothing but, this is the x, and the hypotenuse is going to be square root of all of that. Now if you think about it, in this right angle triangle, right, in this right angle triangle, what would, if I call this angle theta, what is cos theta? Cos theta is going to be exactly this, adjacent side by the hypotenuse, divided by the hypotenuse. And that's nothing but the left hand side. And what about a triangle that you could form here? What can you say about this? And as you can observe, this is nothing but x2 minus x, the adjacent side here, and the hypotenuse is again the square root of x2 minus x squared, y2 squared, and z1 squared, right? Or z2 squared it is rather. Right? Or is it, yeah, z squared it is. And z, as we know anyway, is 0, so it doesn't matter. So it is a z squared. So what we end up with is cos of, if I call this alpha, let's say. So what is cos of alpha? It's going to be x2 minus x divided by square root of all of that. x2 minus x squared, y2 squared, and z squared, which is nothing but the right hand side. So what we have is therefore cos of theta to be same as negative of cos of alpha. You could in fact take a negative sign inside and perhaps write it as cos of minus alpha, but that's not really significant. What's important now is that cos theta is nothing but sine theta 1, because theta and theta 1 are complementary angles, as you can observe. So cos of theta is going to be same as sine of theta 1, and cos of alpha is going to be same as sine of theta 2. And what does this mean? If sine of two angles are equal, sine of theta 1 is same as sine of theta 2. Theta 1 and theta 2 themselves should be equal, except for the sine, of course. But the angles are equal. Angle of incidence is equal to angle of reflection. And that's exactly the second law. So what we have arrived at here is the second law of reflection. So this, I think, is something very significant, because this is both a confirmation of Fermat's principle as well as the two laws of reflection, and particularly it's a consistency between the two. If Fermat's principle, which is purely a theoretical idea, which has of course been deduced from experimental observations, but it's theoretical that light always takes the path that is the quickest. And on the other hand, we have the laws of reflection, which deal with what are the angles forming and how does light bounce exactly when it hits a surface. And now we have a confirmation between the two. You can start with Fermat's principle and deduce the two laws of reflection, and you can do maybe vice versa. You can go from laws of reflection to Fermat's principle. But the important thing to note here is that it is by minimizing that integral of time, that we have been able to arrive at these two laws. So I think this was extremely satisfying, because the two principles that we are aware of, on the one hand Fermat's principle and the other hand the laws of reflection, they seem to be agreeing with each other. And this is a beautiful thing that comes out of this. So that's it for today. In the next video, we will be discussing more such situations and problems that require either minimizing of an integral using the methods of calculus of variations, or the use of the Euler-Lagrange equation. So thank you for watching. Make sure to hit like and subscribe, and I'll see you in the next video. Thank you.